Hi, I'm Benjamin Ryan, and this presentation outlines the process and progress of my 2D clay carving project. The intended artifact for this project is a modular clay tile system that explores carved surface textures. The tiles are designed to repeat while still allowing for subtle variation, creating parametric compositions across a larger surface. The intended material for this project is stoneware clay, chosen for its durability and suitability for carving processes, as well as its final aesthetic. The workflow begins with concept development, where carving gestures are explored and translated into tool paths. This is followed by clay preparation, where slabs are formed and conditioned for carving. The robotic carving process is then applied before the tiles are shaped and left to dry. This workflow aims to connect traditional carving gestures with digital fabrication methods. To evaluate this workflow, I developed a testing strategy focused on key variables. These included carving length and depth, tool spacing, and the clay's condition. The goal was to understand how these variables influence repeatability, surface texture variation, and carving consistency. Testing was conducted through both hand-carved and robotic carved prototypes to allow for direct comparison between manual and digital processes. The hand-carved prototype acted as a baseline for this project. This was completed using wet clay, which allowed for a high level of control and responsiveness. One of the main advantages of this method was the ability to make real-time adjustments based on how the material behaved. However, the results showed less consistency, with noticeable variation in carving depth and spacing due to the manual process. This highlighted both the strengths and limitations of hand-based carving. The robotic prototype explored how these carving gestures could be translated into a digital workflow. Curve profiles were generated and adjusted through scripting with a focus on repetition and consistency. A loop tool was used as the end effector to replicate the scooping and carving gesture. Compared to the hand-carved tests, the clay was in a firmer condition to improve stability during the robotic carving. This setup aimed to create controlled and repeatable surface patterns. The robotic carving produced highly consistent and repeatable surface patterns across the tile. One of the key strengths of this process was the ability to maintain uniform depth and spacing throughout the carving sequence. Unlike the hand-carved prototype, each pass of the tool followed the exact same path, resulting in a much more controlled and predictable surface outcome. This level of precision is particularly important when considering modular tile systems where consistency between units is required for successful alignment and repetition. However, several material-related issues became apparent during testing. When the carving depth was increased, the clay began to drag against the tool, particularly in areas where the tool changed direction. This resulted in rough edges and occasional tearing across the surface. In some cases, clay also adhered to the end effector, which disrupted the cleanliness of the cut and required post-process cleanup. This indicates that whilst the robotic system is precise, it is still highly dependent on the condition of the material. The firmness of the clay played a significant role here. While firmer clay improved stability during the carving, it also increased resistance, which contributed to dragging during deeper cuts. These results highlight that robotic fabrication is not purely a digital process, but one that must be carefully calibrated in response to material behavior. Comparing the hand-carved and robotic prototypes highlights a clear contrast between expressive and controlled making processes. The hand-carved prototype demonstrates a high level of responsiveness to the material, as the carving process adjustments can be made in real time based on resistance, moisture, or surface feedback. This allows for more expressive and varied surface qualities, as each gesture responds directly to the clay. However, this also introduces inconsistency. Variations in pressure, angle, and movement result in uneven depth and spacing, making it difficult to reproduce the same pattern across multiple tiles. In contrast, the robotic prototype prioritizes consistency and repeatability. Toolpath is predefined, meaning each tile can be produced with the same depth, spacing, and pattern. This is highly beneficial for modular systems, where alignment and repetition are essential. However, the robotic process lacks adaptability. Once the toolpath is set, the system cannot respond to unexpected changes in the material, such as variations in moisture or resistance. This can lead to issues such as dragging and deformation that would otherwise be corrected during hand carving. This comparison highlights a key tension in digital craft, the balance between control and responsiveness. While robotics enables precision and scalability, traditional hand processes offer adaptability and material sensitivity. The project sits between these two approaches, exploring how robotic systems might replicate gestures while still engaging with material behavior. Several key findings emerged from the testing process, particularly in relation to how digital parameters interact with the physical behavior of clay. One of the most significant observations was the impact of carving depth. Increased depth of the cut often resulted in tearing or deformation on the clay surface, especially when the material was too soft. This suggests that there is a threshold where the material can no longer maintain clean edges under pressure. Clay condition also played a critical role. The softer clay allowed for smoother carving but introduced issues such as sticking to the tool and loss of detail. In contrast, the firmer clay maintained sharper edges but increased resistance, leading to dragging during more aggressive cuts. The tool interaction was another important factor. The loop tool was effective in removing material, but its shape also contributed to the accumulation of clay during deeper passes, which affected the surface finish. Comparing hand and robotic processes reinforced that hand carving is more responsive to these material conditions, allowing for adjustments during the process. Robotic fabrication, while precise, requires careful pre-calibration of parameters to avoid failure during execution. Overall, these findings demonstrate that successful digital fabrication in clay is not only dependent on toolpath accuracy, but also on a strong understanding of material behavior and its limitations. This reinforces the idea that digital craft is a hybrid process where computational control and material sensitivity must be balanced. Based on these findings, the workflow has been refined to improve both consistency and surface quality. Adjustments include refining the script parameters and optimizing toolpath spacing and controlling the carving variation. The aim is to maintain repeatability while still introducing subtle expressive qualities into the surface design. This refined workflow provides a more stable foundation for further development. In conclusion, this project demonstrates how robotic fabrication can extend traditional ceramic carving practices by translating hand gestures into controlled, repeatable processes while still engaging with the material behavior of clay. Thank you.